Hello there. All right, we're going to go ahead and jump into lesson 11.1. I'm going to need you to go ahead and pause the video and get out 2 pages for this lesson, page 593 and 595. With lesson 11.1 and 11.2 that you guys will be doing on Wednesday, they are going to be talking about, and we're going to be talking about line plots. And line plots are similar to like a graph. It's a way that you can collect data and represent it. So all of the data that we'll look at today and throughout this week will be represented in line plots. Here you see a line plot, and the definition of a line plot is that it shows data along a number line. Each dot above a point on the line represents one number in the data set. Sometimes that represents one number. Sometimes the dots stand for and represent one person. Like if we were going to take and collect some data, we might collect data in our class about the number of siblings that people have or their favorite type of ice cream. And then we could collect that data, make a line plot, and plot our points. Over here you see a vocab word, and we're going to call this the outlier. This is very important. An outlier is any number in the data set that is very different from the rest of the numbers. As you see here, 10 is very different than the numbers represented here on 2, 3, 4, and 5. Okay, I'm going to kind of show you an example. Like if we had 7 plotted here, we would not consider 7 to be an outlier. Remember, the key word and the key thing to remember with an outlier is any number in the data set that is very different. 7 is not very different from 5. However, 10 is. 10 is very different from 5, 4, 3, or 2. Over here at our line plot, you see that there are no outliers. We could create an outlier if we plotted a point at 10 or if we plotted a point farther out on that line plot, but this line plot does not represent outliers. So not every line plot has an outlier. All right, we're going to go ahead and jump into the lesson and take a look. So your lesson today, you guys are going to have line plots and then questions that follow those line plots. They will look very similar to here. Remember, this is just our guided practice and our independent practice before I give you the lesson. So how many giraffes are 14 feet tall? This line plot represents giraffes' heights. So each dot represents one giraffe. The numbers you see here represent feet for the height of that giraffe. So when they ask us how many giraffes are 14 feet tall, we look at 14 and we count the amount of dots. We see 2. So 2 giraffes. Oops, I'm going to have to spell that right. Going on to 4, what is the most common height? So what do you see on the line plot that is represented the most? What height is represented the most? Well, there's 2 giraffes measuring 14, 3 measuring 15, 2 16, and 2 18. So that would tell us that 15 is the most common height. How tall is the tallest giraffe? Well, tell me what number is the largest. That's going to be the tallest giraffe, and that is 18 feet. Is 18 feet an outlier? That's a really good question. It's also a tricky question, and you've got to ask yourself, the definition for outlier is any number in the data set that is very different from the rest of the numbers. Is 18 very different from 16? I would say no, it's only 2 away. Your outlier are going to fall anywhere from 4 to 10 data points or plots away. So is not 18 feet an outlier? We're going to say no. 18 feet is similar to the other lengths. Okay, and looking down at the bottom, I'm going to fold my page for you guys so it's a little bit easier to see. Okay, another line plot. This represents times for a 100-meter sprint. And everything down here is in seconds. You will notice that these are mixed numbers. You've got a whole number and a fraction. So it starts here with 10 seconds and over here ends at 11. So when it asks us how many people ran the 100-meter sprint, each of these dots is going to represent one person. So I'm going to go ahead and count that, starting over here at 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And hopefully you count and double check me. So 20 people. And then which time was the most common? What time do you see the most people that it took the most people to complete the 100-meter sprint? Okay, and it's pretty easy to look at it here. All the data is pretty close together. I would say the most common time was the 10 and 4/10 of a second. Okay. What time is an outlier? So what time is very different from the set of numbers? Okay, you see here that 11 is 2 points away from our 10 and 7/10. So you could identify 11 as our outlier, 11 seconds. Number 10. How many more people ran the 100 meters in 10 and 6/10 seconds than in 10 and 1/10 second? So first, what you're going to do when you have any problem that looks like this, you're going to want to say, okay, well, how many people ran in 10 and 6/10 seconds? So go find 10 and 6/10, 1, 2, 3. You can go ahead and just write a little number up there or bring it down here and write it below the 10 and 6/10. Then in 10 and 1/10 second. Well, in 10 and 1/10 second, that's only 1. So when it asks us how many more, that how many more is going to tell us what are we going to do with 3 and 2. Or 3 and 1. Sorry, guys. We're going to subtract. 3 take away 1 equals 2. So how many more people ran in the 100 meters? Or ran the 100 meters in 10 and 6/10 second than in 10 and 1/10 second? That would be 2 people. All right. Curtis says that more than half of the people ran 10 meters in less than 10 and 4/10 seconds. Do you agree? Okay. So you've got to think here. And read it again. I'm going to read it again because I need to for clarity. Curtis said that more than half the people ran 100 meters. So first off, tell me, what would half of the people be? What number would half of the people who ran the race be? If a total of 20 people ran the race, what is half of that amount? That is 10. So he's saying that more than 10 people ran 100 meters in less than 10 and 4/10 seconds. So does that 10 and 4/10 second include when it says less than? No, it doesn't. That means all of the numbers that are less than that 10 and 4/10. Do you agree? Well, let's count. Let's see how many people finished the race in less than 10 and 4/10. 1, 2, 3, 4, 5, 6, 7, 8. So do we agree? I would say no. Okay, only 8 people finished the race in less than 10 and 4/10 seconds. Okay, guys, I don't want you to be worrying or freaking out right now. Okay, if you're kind of confused, don't worry. Take a deep breath. You'll take a look at your assignment. If you need help, you know that I'm on in the afternoons. Okay, let's turn this around. We're not going to worry about this. I just want you guys to get a few more practice problems in. So let's take a look down here. So when it asks us, remember an outlier, those numbers that are very different than the rest of the set of numbers. So is there an outlier? Looking here at the nails in Ed's toolbox. Is 3/4 an outlier? Is 1 2/4 an outlier? Is 2 inches an outlier? You see that none of these are very different than the rest of the set. So we would say there is no outlier. Remember, there doesn't always have to be an outlier. Okay. Which length of nail is most common? That means what shows up the most. How many, okay. Where do you see the most dots? Let me ask you that. What length in inches? That would be your 1 2/4. So there was 4 there. That would be C. Okay? All right, so now for our lesson, I'm going to do a few of the problems with you guys. Okay, but here's our homework and practice 11.1. This is page 595. You're going to go ahead and do the whole front and back. But we're going to do all of the ones that I have circled because those are the ones that I found most difficult. Okay, it says for 1 through 5, use the line plot at the right. So we're looking at the weights of puppies in a pet store. Okay, you're going to look at for any outliers, what weight is most common, how many more puppies weighed 3 pounds than 7 pounds, how many puppies weighed less than 7 pounds, and what is the total weight of all the puppies weighing less than 6 pounds. Okay, so again, think about less than 6 pounds, that's right here. So the total weight of all of the puppies weighing less than 6 pounds. Well, first what we're going to need to do is we're going to need to find out how many puppies weighed 5 pounds. 2 puppies weighed 5 pounds. How many puppies weighed 4 pounds? 3 puppies weighed 4 pounds. How many puppies weighed 3 pounds? Sorry. 5 puppies weighed 3 pounds. Okay, so we're trying to find the total weight of all of the puppies. Well, first off, how much is the total weight of the 2 puppies that weighed 5 pounds? What are we going to do with 2 and 5? If there were 2 puppies, they each weighed 5 pounds, we're going to need to multiply. That gives us 10 pounds. And I'm going to abbreviate that with the LBS. Okay, we've got 3 puppies that each weighed 4 pounds. So again, we're going to need to multiply. That gives us 3 times 4 is a total of 12 pounds. And then we've got 5 puppies each weighing 3 pounds. Again, multiplying. And now to answer what is the total weight of all of the puppies. That's where we're going to go ahead and add. 2 plus 5 is 7, and 1 plus 1 plus 1 is 3. The total weight of all of the puppies is 37 pounds. Okay? Taking a look at the back. Okay? Is there an outlier for the data in this line plot? Okay, this line plot's looking at the heights of students in Miss Jackson's class. Do you see any that are very different than the rest? I would say no. Okay, there is no data point that is far away from the rest. And you can pause this if you need to copy this down. Go ahead, let's look at number 8. Okay, we're looking at heights of house plants. So these are, all these dots represent plants. It says based on the line plot, how many more plants are less than 3 2/4 inches then are greater than 3 2/4 inches. Okay, so what we need to do here is find the amount of plants that are less than this 3 2/4 and that are greater than the 3 2/4. Now you'll realize it doesn't include the actual plants that are measuring 3 2/4. So for this problem, we're not needing it. I'm not going to cross it out because I don't want you to for your next question. Okay, but we've got to figure out how many are less than. Well, let's count them up. 1, 2, 3, 4, 5. We've got 5 that measure 3 1/4. 1, 2, 3, 4, 5 that measure 3. So how many are less than 3 2/4? We could add to find that out. Okay, that's a total of 10 plants measure less than. How many plants measure greater than? We've got 2 and 2. It's a total of 4. Okay, 4 that are measuring greater than. So it's asking us how many more. Again, we are having that same, how many more. So we're going to need to subtract here. How many more are less than 3 2/4 inches than are greater than 3 2/4 inches, which is 4? 6. 6 plants. Okay? Again, your assignment is all of these, front and back, 1 through 11. Good luck, and let me know if you need any help.